Welcome to This Explainer. Today, we're unpacking a massive technological shift happening literally right beneath our feet. For those of you in the agricultural sector, you already know the immense pressures the industry is facing right now: soaring fertilizer costs, severely degraded soils, and increasingly strict regulations. But today, we're going to explore a groundbreaking paradigm shift derived from our source materials that offers a very real biological way out of these challenges. It's called the Holobiont Paradigm, and it completely redefines how we look at crops and the unseen microbial networks that support them. Here is our roadmap for today. We'll start with a market explosion, move into the dependency trap, introduce the Holobiont concept, break down B&I innovation, and finally, look at archaea differentiation. Let's dive right into Section 1, Market Explosion. Why is this shift happening right now? Well, the answer is incredibly clear when you look at the numbers. The global agricultural biologicals market is projected to hit a staggering $23.9 billion by the year 2035. That is a rapid 117% explosion from the $11 billion market size projected for 2025. We're talking massive growth. For investors and agronomists alike, this is a giant neon sign pointing out that biologicals are moving away from being just a niche alternative, straight to the absolute core of future agricultural strategy. And this explosive growth isn't just some passing trend. It is an unavoidable market shift forced by major structural drivers. Just look at the regulatory pressures. The European Union's farm-to-fork strategy has laid down a hard mandate to slash chemical pesticide use by 50% by 2030. 50%. At the same time, massive retail giants are totally dictating terms. Walmart, for example, has demanded zero pesticide residue from over 2,000 of its suppliers. And the financial world is absolutely reacting to this. In 2024 alone, we saw $1.8 billion in venture capital funding pour into agricultural biotech startups. The market is demanding a massive reduction in chemicals, and capital is flowing straight to whoever can provide the biological alternatives. So what's driving this need for alternatives? That brings us to Section 2, the dependency trap. Modern agriculture is frankly stuck in a vicious cycle. Think about it. We rely heavily on imported chemical fertilizers to drive our crop yields. But over time, all that excessive chemical use degrades the soil, literally killing off the natural microbiome. This dead soil leaves crops totally vulnerable to disease and environmental stress. So what happens next? Farmers are forced to apply even more chemicals and fertilizers just to maintain the status quo. It's a brutal dependency trap that results in skyrocketing external costs and exhausted land. To break this cycle, we can't just try to improve the genetics of a plant in isolation. We have to reboot the entire ecosystem. And that ecosystem reboot is exactly what Section 3 is all about: the holobiont concept. Okay, so what exactly is a holobiont? The holobiont concept means we stop looking at a plant as just a solitary set of genetics. Instead, we view the host plant and its massive community of symbiotic microbial partners as one single integrated functional biological unit. Just as human health relies heavily on our gut microbiome, a plant's health relies on its root microbiome. It's like a bustling microscopic city working around the clock for the plant. They evolve together and they function together. This concept completely shifts our approach to farming. In conventional agriculture, we spent decades trying to improve isolated plant genetics while kind of ignoring the soil. That's what led to our heavy reliance on expensive, environmentally taxing chemicals. But in this new holobiont era, plants and microbes actually team up. By utilizing the entire symbiotic system, you get incredibly high-efficiency nutrient absorption and massive natural resistance to environmental stress. The need for chemical inputs drops dramatically. It's a shift from just treating symptoms to managing a robust, living ecosystem. Now, how does this actually work in the field? Let's get into Section 4, B&I innovation. B&I stands for biological nitrification inhibition. It's a natural process where the plant and the soil are truly working as a team. Here is how it plays out in 4 clear steps. First, the plant roots actively release specific B&I substances into the soil. Second, these substances act like a natural brake. They specifically target and weaken the microbes that cause nitrification. Third, this slows down the rapid conversion of stable ammonia nitrogen into highly soluble nitrate nitrogen. And finally, because that conversion is slowed down, the nitrogen stays right there in the root zone for much longer, allowing the crop to absorb it with incredible efficiency. This mechanism is an absolute breakthrough. Normally, when you apply fertilizer, soil microbes rapidly convert it into nitrate. Then, the very first time it rains, a huge portion of that valuable fertilizer simply washes away as runoff. It's literally money down the drain, and it pollutes our waterways. But in a BNI active holobiont soil, that rapid conversion is blocked. The fertilizer stays exactly where the plant needs it. This natural break is the ultimate trump card for cutting our reliance on imported, expensive chemical fertilizers, because we are finally using every drop we apply at maximum efficiency. Which leads us to the final piece of the puzzle, Section 5, archaea differentiation. For years, ag tech companies have tried adding microbes to the soil, but they kept hitting a brick wall. And we need to be very precise with our terminology here. They were using standard bacteria. Data from UC Davis actually shows that using standard bacteria results in a massive 30% to 70% variance in field reproducibility. Why? Because soil types constantly change, and standard bacteria just can't handle it reliably. Enter the game changer, archaea. Archaea belong to an entirely different domain of life from standard bacteria. They are extremophiles. To put that into perspective, archaea thrive in boiling hydrothermal vents and highly acidic lakes, so surviving the fluctuating, harsh conditions of a farm field, that is an absolute walk in the park for them. This gives them overwhelming biological stability and resilience that standard bacteria simply do not possess. This is exactly how pioneers like T3 are positioning themselves. While commercial giants are still struggling with the unpredictability of standard bacteria, hitting that massive global barrier of field reproducibility, T3 leverages academic frameworks to utilize these highly stable archaea. It puts them in a completely unique, highly commercialized league of their own. By building an archaea holobiont, they are literally solving the biggest technological bottleneck in the entire industry, providing overwhelming stability and reproducible results across totally different soil environments. So how exactly do archaea manage the soil environment with such precision? Well, they don't just directly attack standard bacteria. They brilliantly orchestrate the whole ecosystem. First, through niche differentiation. Archaea outcompete standard bacteria for resources, completely thriving in low-nutrient, harsh conditions where standard bacteria just fail. Second, by integrating into the root network, they indirectly suppress the colonization of harmful pathogens. And third, the biological oxidation driven by archaea actually yields significantly lower greenhouse gas emissions, like nitrous oxide, compared to standard bacteria. They act like the invisible, masterful conductors of a healthy soil orchestra. We've covered a tremendous amount of ground in this explainer today, moving all the way from multi-billion-dollar market shifts down to the microscopic power of archaea. By completely shifting our view to the holobiont and tapping into the power of incredibly stable extremophiles, we finally have a scientifically grounded path to reduce our chemical dependency. Which leaves us with a final, provocative thought to consider. Will fully embracing this unseen microbial world be the key to securing the future of our global food supply? I'll let you ponder that one. Thanks for joining us today.